this segment we're going to talk about Gaussian mixture models, which are often called GMMs. Gaussian mixture models are a way of fitting multiple Gaussians to a set of points which is possibly multidimensional. In that sense, it's a generalization of what we did before in one dimension with binned data, when we took a set of points, binned them, and then fit the resulting histogram with two Gaussians. Here, we don't have to bin the data. We can just use the raw data points. Furthermore, the data can be in greater than one dimension. These can be points in a multidimensional space. However, it does have the disadvantage that the properties of Gaussians are used in detail. It doesn't easily generalize to other fitting functions, for example, fitting components that have tails that decay more slowly as Gaussians. But we'll see the advantages and disadvantages in this segment and in the next one. Gaussian mixture models are also important because they're examples of a very general technique called EM methods, expectation-maximization methods. And in the segment, not immediately after this one, but the segment after that, we'll come back to EM methods in general and show a little bit of theory about them. So let's first do a GMM, a Gaussian mixture model, on one-dimensional data. In fact, it's data that we've seen before. It's the set of exon lengths, or log of exon lengths of the human genome. So here I've binned it now as a histogram just to display it, but really we have the individual points located along this axis underlying this histogram. This is a very long-tailed distribution. You can see even there are outlier events way out here, and there's an event way out here. And it turns out that Gaussian mixture models aren't going to do very well with those outliers. So a good thing to do in this example is to trim the outliers here, giving this better behaved histogram that goes to 0 within a reasonable range on both sides. Now there's a lot of notation in Gaussian mixture models, and I want to go through it in the very general case of multi-dimensions, even though we're only doing a one-dimensional example. So first of all, we need a letter for the number of dimensions. Capital M is the number of dimensions we're in. So right now, M is equal to 1. Then we need to know how many components, how many separate Gaussians we're going to try to fit as we cluster this data. And that's capital K. So in our example here, capital K is 2. We want to find out what is the relative probability that each point lies in this component, component 1, or this component, component 2. Then we need to know capital N, the number of total data points. You can hardly see it along here, but in our one-dimensional example from a previous segment, I think there were about 100 data points along here. And we can label them with little n from 1 to capital N. Now one of the things we're going to try to get out of this model is what is the fraction of the total number of events that is in each component. And we're going to call that P of K. K, as you see up here, indexes the components, and P of K is a probability. It's the probability that a point drawn at random is actually in the kth component. Finally, there's a probability for each point along the line here, or in multi-dimensions, each point that we're given. What is simply the probability within the model that we're going to fit of finding a point at that position. And so that's denoted P for probability of x sub n, the vector position of the nth point. But we're not nearly done yet. There's more notation. Each of these Gaussian components, because it's a Gaussian, has a mean and a covariance. The mean tells essentially where its center is, and that mean is a vector mu sub k, where k tells which of the Gaussian components here this is the mean of. So we actually have capital K vectors, the k means. Similarly, we have capital K covariance matrices, each a matrix of size m by m. So those then completely define the Gaussian components. We also need to know the k probabilities for each of the n data points. That is to say, each data point has a certain probability of lying in each Gaussian component, and that's a matrix of numbers that we'll call Pnk, which is the probability given that we're looking at data point n that it's in the kth component. But wait, there's more. The overall likelihood of the model is simply the probability of the likelihood of each point in the data, and then we multiply all those probabilities together. So we've already defined up here the model probability at each point x sub n. We take the product over the data, and that's the overall likelihood of the model. If we're thinking in frequentist terms, that's what we want to maximize. We want to find the value of all these parameters that maximizes the overall likelihood of the model. Now we haven't yet specified that the probability of the model at a given point is in fact a sum of normal distributions of Gaussians. So here's where we do that. The model probability is the sum over components k, that should be a k right here, of the normal probability distribution at that location with the mean and covariance matrix appropriate to the term in this sum. And then those are weighted by the overall probability that the point lies in that component, which is to say up here the population fraction in k. The notation n here for normal distribution is defined here in the usual way, that the normal distribution evaluated at point x in terms of its mean and covariance is the familiar multivariate normal here. The notation has changed a little bit from previous segments. I'm using the dot notation here instead of putting a matrix transpose here. And what do we want? Our goal is pretty ambitious. Our goal is to find all of the above quantities, starting only with the list of vector positions of the data points x sub n. Now, as you've seen so far, this could be a frequentist argument. It could be a maximum likelihood kind of calculation. And in just the way that we've seen previously, it could also be a Bayesian calculation where there's some kind of uniform prior underlying this. In fact, GMMs were invented by frequentists, so we tend to use their language for it. Now, how do we find all of those quantities? We don't know where to start. We're just given a list of points. The key observation is that we can partition the problem into two kind of hypotheticals that then interplay in a very useful way. So the first piece of this is called the expectation or E step. And the E step says, suppose we know the model, we know the Gaussians, we know their location, their means, and their covariance matrices, and we even know what their relative weights are, what the p of k's is, the probability of a point lying in each of the Gaussians. Then we know enough to calculate for each point, little n, its probability of lying in component k. And that probability is simply the weight in component k, that is to say the normal distribution evaluated at that point's position, times the weight of component k, and then it's a Bayesian denominator down here. It's divided by the sum of these numerators over all k, because if you go back to the previous slide, you'll see that that's how p of xn was defined. It was simply the sum of the normal densities over all the components. So this fraction, one component over sum of all the components, is the probability that a point lies in that component. Well, you say that doesn't do us any good because we don't know the model. We don't know the locations of all the components. That's where the M step or maximization steps comes in, because that's exactly the other way around. It says, suppose we know the assignment of the individual points, but we don't know the model. And here's where we use this property of Gaussians that we've discussed before, that it's very easy, given a set of points in a Gaussian, to fit for which Gaussian it is. You essentially compute the mean, an estimate of the mean of that Gaussian, as the average of the location of all the points in it. Well, here it's a weighted average because we don't know exactly which points are in it, but we simply compute the weighted average, or centroid, summing over all the points of its vector position times the weight, the probability that it is in that component, p of nk, and then we of course divide by the sum of the weights here to get the weighted average. Similarly, we can compute the value of the covariance matrix, the estimate of the covariance matrix, by just an average of this matrix quantity. Again, I'm using a slightly different notation from previously. If you want this in matrix notation, you would take out this outer product sign and put a transpose on this matrix, so that this becomes one term in the sum of our estimate of covariance matrices. And finally, if we want to estimate the fraction of population in each component, well, we just take all the points and we add up the probabilities over all the points n of there being in that component k. And since we want these p of k's to be normalized to add up to 1, we divide by 1 over the total number of points. So if we could do this step, then we could do this step. If we could do this step, then we could do this step. The important theorem that we're going to discuss theoretically in a couple of segments from now is that if you iterate going back and forth between these steps, the overall likelihood of the model always increases. And that's an iterative way of solving the whole model. In fact, it can be proved that alternating E and M steps converge to at least a local maximum of the overall likelihood. But you have to be a little bit wary because the convergence can be very slow with long plateaus. So there are various ways of speeding up EM methods, but for the basic method, just converge for a long time before you decide that you're done. How do you get started? Often people get started by choosing k random data points and just assuming that they are the centers, the mean values of the k components, and then starting with equal, usually spherical covariance matrices. Of course, you're only going to use those assumed values for one step because you're immediately going to go up here and do an E step, then come back and do an M step. Now there are a couple of tricks if you ever want to really implement your own GMM code. A couple of tricks you should know. The first trick is you're going to be evaluating things way out on the tails of some Gaussians, and you don't want those to underflow and you end up in a position where you are trying to compute 0 over 0. So it's best never to store the actual value of a normal distribution, but only to store its log, which is of course the stuff that's in the exponent of the normal distribution, and then that stuff that's outside the exponent you force into the log by just taking the log of it in the appropriate way. You can work that out. But you say, I can't work completely in log space because I have to do this operation. I have to do a sum over normal distributions times something here, but in any case a sum over things which I need the thing, not just the log of the thing. And here's where a very useful little formula, trivial in a way, but very useful, the log sum x formula comes in. And this is just an identity. It says that if you have a bunch of things zi's in log space, and you want to get them back into regular space, so you take the exponential, and then you want to take a sum of those exponentials and put it back into log space, because that's essentially what this operation up here is going to be. Well, it's simply an identity that if you search through all the values zi for the maximum of those values, and then you subtract that maximum value from each of the ones individually. Well, let's look at this expression. E to the zi times e to the minus z max. So there's a common term of e to the minus z max in this sum. We can pull that out of the sum, and then in the log that just makes a minus z max additively. So if we add a z max back in, then we'll see that the left hand side and right hand side is equal here. Well, what did I accomplish by that? You'll see that what I accomplished by that is I'm pulling out the dominant term in the log sub x, and then all these other terms are all 0 or negative because the zi is less than z max. And then if these exponentials underflow, I don't care because I've already gotten the dominant term. And of course, in general, most of them won't underflow, but some of them will, and you just don't care. So these are tricks. We're actually going to skip these tricks in our one-dimensional example, but in the next segment, in Numerical Recipes 3rd edition, they are implemented, and we're going to use that code. So let's just quickly do our one-dimensional example here. The E step, that's where we evaluate the relative probabilities of the points, looks something like this, and here I'm in MATLAB code. The E step requires that I know the positions of the components, the means of the components, and this is a 2-component model, and I'm going to assume that the two means are at 2, that's kind of here, and at 3, that's kind of here. And I'm going to assume that I know standard deviations. I've just made up these numbers as starting points. Okay, and then here's where we compute the value of the normal distribution. We actually don't have to have the normalization constants in front, right, because we're going to do the Bayes denominator thing to get the normalization. And just for fun, I've computed the two probabilities. Suppose I had an event at 2.5, one of the events that falls into this bin. Then its relative probabilities of being in the first component versus the second component are in the proportion of these values here. But I need to normalize them, so here I'm going to define a new little function, which is the old function, and then divided by its sum, so that normalizes it. And if I now compute this normalized value at 2.5, I find that for a point here in this bin, it has a 16% chance of being in the left component and an 83% chance of being in the right component. Okay, now I need to just compute the whole matrix of these probabilities over all the data points. Here I'm just going to show you a list of 10 data points from 100 to 110, and you see they vary all over the place. Here's a data point that has a 96% chance of being in the left component and a 3% chance of being in the right component. Here's one that's the other way around. It's dominantly in the right component and only a small probability in the left component, and so on. So that's the E step. Now the M step is just that step where we take the weighted average of those positions and find the mean and standard deviation of each component. And I've done that here in sort of the elegant MATLAB data parallel language, which unfortunately makes the code a little hard to read with these rep mats, repeat matrices, and so on. So I'll let you puzzle this out, or else recode it yourself in your own favorite computer language. Unfortunately, this simple data parallel version of the code doesn't generalize to multi-dimensions anyway, and that's part of the reason I'm not going to bother to teach it all to you here. But let's now show 10 iterations of the EM steps. So here's my loop from 1 to 10. I'm starting with the starting values, and as I said, I'm guessing for a mu, a mean of each starting Gaussian, simply the value of the mean, that's component 1, for a randomly sampled piece of data, and then a different randomly sampled piece of data, in other words, data point here, and I'm just guessing standard deviations here. Well, this is code you've seen before. This is the E step, and then this is the M step, and then this stuff is to produce the plots that I'm going to show you on the next page. I'm going to plot what the fit looks like after each iteration so that you can show it so that you can see it converging. But what are you going to see it converging to? Well, it's supposed to converge to that histogram that I showed you on the previous page, but we don't have a histogram here, we just have the raw data points. Well, MATLAB has a function called kernel smoothing density estimate that's some kind of estimate of the distribution function when you have a bunch of data points, and I'm going to use that just in the plot. I wouldn't trust it any further than that unless you really look into what kernel smoothing is and convince yourself that it's what you want for your problem. Anyway, here's the answer with two components. We start with this lower curve here, And then with each successive iteration of the EM, these happen to go in order, and we converge to the sort of upper envelope here, which you'll see as you come down here is this curve here. Look, it misses the red curve. It doesn't do very well, and then it comes out here, where the red curve is supposedly the smooth kernel density estimate that we're trying to converge to. Notice that Gaussian mixture models make a completely different set of compromises from alternative fitting methods in one dimension. In particular, no matter how long I converge this thing, this shoulder here is not going to come down to its true value or better approximation of its true value here. And the reason is because the tails of the data are not Gaussian. And a Gaussian mixture model just hates to miss in those tails because it's going to miss them by kind of orders of magnitude in likelihood. Whereas here, if it accepts this rather bad compromise, it's missing by only some fraction of 1 in likelihood. Okay, so that's not a good property of Gaussian mixture models. It's something you should be aware of. The way you get around that is you simply start adding components. So here's exactly the same data fitted now by 3 components, starting here and converging to the peak up here, which now you'll see does a tolerably good job of fitting this tail out here. In fact, more components generally converge to an excellent approximation of the data. However, that doesn't mean that those components are anything physical. That's a mistake people sometimes make. Just because you have a very good fit when you put in 5 components or 10 components or 15 components does not mean that there are 5 or 10 or 15 separate physical things going on, each producing a Gaussian. You should probably view Gaussian mixture models much more as a fitting interpolation method than you should view them as a way of getting at the underlying question of how many components are truly in my data set. Now in this example, I should also comment, almost all starting points give the same ending converged curve here, and so presumably that is in fact the global maximum likelihood curve. There's no easy way to check that. However, in multi-dimensions, that's not always true, as we'll see in the next segment, and so it's a very good idea to start from multiple starting points and see if you converge to the same curves.